Welcome back, tech enthusiasts, to another exciting episode of Operating Systems Crashcast. I'm your host, Victor, and as always, I'm joined by the brilliant Sheila. We're continuing our journey through Season 1, which provides an overview of operating systems, and we're still in Chapter 1, Introduction.
That's right, Victor. In our last episode, we dove into what operating systems do, covering their role as resource managers and providing an abstraction layer for hardware. Today, we're moving on to Section 1.2, Computer System Organization. This is where we'll get into the nitty-gritty of how computer systems are structured and how that relates to operating systems.
Absolutely, Sheila. Before we dive in, let's start with a quiz question for our listeners. Here's the question. What is the primary purpose of interrupts in a computer system? Keep that in mind as we go through the episode, and we'll reveal the answer at the end.
Great question, Victor. Now let's start by breaking down the fundamental components of a computer system. At its core, a modern computer system consists of one or more processors, also known as CPUs, main memory, and various I/O devices, all connected through a common bus providing access to shared memory.
That's a great starting point, Sheila. You know, I like to think of a computer system as a bit like a car. The CPU is like the engine, the main memory is like the fuel tank, and the I/O devices are like the steering wheel, pedals and dashboard. The bus would be like the car's frame, connecting everything together.
That's a clever analogy, Victor. It really helps visualize how these components work together. Let's focus on the CPU for a moment. The CPU is the brain of the computer, executing a series of instructions that make up a program. It operates in a fetch, decode, execute cycle, constantly retrieving instructions from memory, figuring out what they mean, and then carrying them out.
Exactly right, Sheila. And just like how a car engine needs to know when to shift gears or when the driver wants to stop, the CPU needs a way to handle external events. This is where interrupts come in. An interrupt is a signal to the CPU that an event has occurred, requiring its immediate attention.
Interrupts are crucial for efficient operation of a computer system. They allow the CPU to respond to important events without constantly checking for them, which would waste a lot of processing power. For example, when you press a key on your keyboard, it triggers an interrupt, telling the CPU to process that input.
That's a great point, Sheila. Interrupts can come from various sources: hardware devices, software errors, or even the CPU itself. When an interrupt occurs, the CPU temporarily suspends its current operations, saves its state, and executes a specific routine called an interrupt handler. Once the interrupt is handled, the CPU resumes its previous task.
Now, let's move on to memory, another crucial component of computer system organization. Modern computer systems use a memory hierarchy with multiple levels of storage varying in speed, size, and volatility. At the top of this hierarchy are the CPU registers, which are the fastest but smallest form of storage.
Right? And then we have cache memory, which is slightly slower but larger than registers. Main memory, or RAM, comes next, offering even more storage but at a lower speed. Finally, we have secondary storage devices like hard drives or SSDs, which provide large amounts of non-volatile storage but are much slower to access.
Exactly, Victor. This hierarchy is designed to balance speed and capacity. The operating system and hardware work together to ensure that the most frequently accessed data is kept in the faster storage levels. It's a bit like how you might keep your most used tools within arm's reach, less frequently used ones in a nearby toolbox, and rarely used ones in the garage.
That's a great way to think about it, Sheila. Now let's talk about I/O devices. These are the components that allow the computer to interact with the outside world. Things like keyboards, mice, displays, disk drives, and network interfaces. Each I/O device has a device controller, which is a chip or set of chips that physically controls the device.
And these device controllers are crucial, Victor. They provide an interface between the device and the computer system, handling the low-level details of controlling the hardware. The operating system then communicates with these controllers through device drivers, which are software components that understand how to interact with specific types of hardware.
That's right, Sheila. And here's where we get into an interesting concept: direct memory access, or DMA. In early computer systems, the CPU was responsible for transferring data between memory and I/O devices, but this was inefficient, as it tied up the CPU with simple data transfer tasks.
Exactly, Victor. DMA was introduced to solve this problem. With DMA, certain hardware components can access memory independently of the CPU. This allows for much more efficient data transfer, especially for high-speed devices like network cards or disk controllers.
Let's use our car analogy again. If the CPU is like the driver, then DMA is like cruise control. It allows certain operations to happen automatically without constant intervention from the driver, or in our case, the CPU.
That's a great way to put it, Victor. DMA has become increasingly important as I/O devices have gotten faster and faster. Without it, our modern high-speed computers would be significantly bottlenecked by I/O operations.
Absolutely, Sheila. Now let's take a moment to consider the historical context of computer system organization. In the early days of computing, systems were much simpler. They often had a single CPU, a small amount of memory, and very limited I/O capabilities.
That's right, Victor. The concept of interrupts, for instance, wasn't present in the earliest computers. Programmers had to explicitly check for I/O completion, a technique called polling. Interrupts were a significant advancement, allowing for more efficient use of CPU time.
And memory hierarchies have evolved dramatically too. Early computers had only main memory, and maybe some form of secondary storage like punch cards or magnetic tape. The introduction of cache memory in the 1960s was a game-changer, significantly improving system performance.
Absolutely, Victor. And it's worth noting that while the basic principles of computer system organization haven't changed much, the implementation has advanced tremendously. Today's multi-core processors, gigabytes of RAM, and blazing fast SSDs would have been unimaginable to early computer engineers.
That's so true, Sheila. And these advancements have had a profound impact on operating systems. Modern OSes have to manage much more complex hardware environments, dealing with multiple CPU cores, various levels of cache, and a wide array of high-speed I/O devices.
Exactly, Victor. The principles we've discussed today, CPUs, interrupts, memory hierarchies, I/O devices, and DMA, are all fundamental to understanding how operating systems interact with computer hardware. They form the foundation upon which all of an operating system's more complex functions are built.
Well said, Sheila. Now let's wrap up with a quick recap. We've covered the basic components of a computer system: the CPU, memory, and I/O devices. We've discussed how the CPU operates and the crucial role of interrupts. We've explored the memory hierarchy and how it balances speed and capacity. And finally, we've looked at I/O devices and the importance of DMA for efficient data transfer.
That's a great summary, Victor. And now I think it's time to answer our quiz question. Victor, can you remind our listeners what the question was?
Of course, Sheila. We asked, what is the primary purpose of interrupts in a computer system?
Ah, yes, great question. The primary purpose of interrupts in a computer system is to allow the CPU to respond quickly to important events without having to constantly check for them. Interrupts enable efficient multitasking and timely response to external events, such as user input or the completion of an I/O operation. They're a crucial mechanism for balancing the CPU's attention between various tasks and events in the system.
Excellent explanation, Sheila. I hope our listeners found that informative. And that brings us to the end of today's episode on computer system organization. We've covered a lot of ground, but remember, this is just the foundation. In future episodes, we'll build on these concepts as we delve deeper into the fascinating world of operating systems.
Absolutely, Victor. And to our listeners, thank you for joining us on this journey through the fundamentals of computer systems and operating systems. We hope you're finding these episodes informative and engaging. If you are, please don't forget to subscribe to Operating Systems Crashcast. We've got plenty more exciting topics coming up.
That's right, Sheila. In our next episode, we'll be diving into computer system architecture, where we'll explore how these components we discussed today come together in different system designs. Until then, keep your systems running smoothly.